Welcome to a lesson with Dr. Pal. In this video, we will take a look at an application problem similar to the last one. We have a curve and a point. I'm just giving an example of the same thing, but I'm going to go a little bit more quickly through it. Please look at the last video to see specifics and details. I'm just going to walk through this one. Okay, so we're going to be finding the minimum distance between this point and this curve. Points on this curve look like x, 2x squared plus x plus 1. We want to find the minimum distance, so the minimum output of a function that describes distance between these 2 points. But we're going to simplify that to just be looking at the minimum square of the distance, so we're not dealing with square roots. Thinking of a Pythagorean theorem, to get distance, you think difference of y's, difference of x's. Difference of y squared plus difference of x squared. Square rooting would give you the distance, but we're going to ignore the square root, and we discussed that in the last video, because if you minimize what goes into the square root, you're minimizing what's coming out of it. So we have difference of x's, x minus 6 quantity squared, plus difference of y's, 2x squared plus x plus 1 minus 3 squared. So if let's just minimize this as a function. All right, so we'll just start by taking a derivative using the chain rule. 2x minus 6 plus, use the chain rule here, we're going to simplify that to a negative 2. 2, so the power comes down, 2x squared plus x minus 2. Then you have to multiply by the derivative of the inside, which is 4x plus 1. Okay, and right away I'm not really seeing how, and there doesn't look like there's any common factors other than this 2 here. I could pull out the 2 out of everything, or even just ignore it. If I'm trying to find places where the derivative is equal to 0, the factor of 2 is never going to be 0. So in this sense, we're just going to ignore the 2, and if we're looking for critical points. And so, because 2 is a common factor of this whole bit right here, and this whole bit be factored out, and just ignore it just off the side. So I'm going to just pretend like it's not there for a minute and just write x minus 6 plus, and then let's just multiply this to this. And if you want, I have a video on multiplying polynomials, or multiples of, maybe multiple videos. But one way we can do this is simply by thinking, think of place values, but with like powers of x. But remember, never carry. But that's just because you can't group by powers of x like you can with powers of 10 with different values here. Because really, when we multiply things, think of our regular base 10 digit system, you think we really do this all the time, because every number can be thought of as a polynomial, powers of 10, like times 10 times 10 squared and so forth. Really, our multiplication algorithm works well for polynomials as well. Just remember not to carry. 1 times all of this, but never carrying, so you can just say 1 times this list here and just plop it down, 2, 1, negative 2, and then you move over here. But you're going to be shifting things over, because this is a power of, this is just times x, so it shifts everything over a place value of x or a power of x. So 4 times this lot just shift it over. 4 times negative 2 is negative 8. 4 times 1 is 4. 4 times 2 is 8, and I'll squeeze it in right there. Okay, then just add down. So you get negative 2, negative 7, is that 6 and 8. And think of this as constant, power of x, x squared, and x cubed. That's just kind of a fast way of going through that if you want here. Remember, the 2's have been blown out of the water because we factored them out, and we're ignoring them because it'll never be equal to 0 in our derivative. All right, so plus, and then we have 8x cubed plus 6x squared minus 7x minus 2. All right, we can combine a couple things. This x and that become minus 6x. Negative 6 and negative 2 becomes a negative 8. Then we have 6x squared, and we have 8x cubed, just like this. Right. Okay, and actually it's kind of nice. We could factor it a 2 at this stage. That's kind of nice. Another 2. Or even divide by 2, because we're just trying to figure out where this is equal to 0, right? And the 0 will swallow and divide both sides by 2. So we end up getting, let's just do that first. If we divide everything by 2, that'll be 4x cubed plus 3x squared minus 2x minus 4, like that. Yeah. Okay, let's see, is that right? Minus, 3, sorry. Ha! Yeah, that's important. Okay, divide by 2, 6. Sorry about that. 6 divided by 2 is 3. So you get 4x cubed plus 3x squared minus 3x minus 4. Now you see this negative 3 and negative 4 and positive 4, positive 3. What if, just by observation, notice that if we just stuck a 1 in everywhere, you get 4 plus 3 minus 3 minus 4. That's 0. Hey, that's a solution. Hey, that means x minus 1 is a factor. Now that was done on purpose a little bit, maybe. But this video also supplies some practice with factoring polynomials here, if you know one of the factors. Here, if we think of a synthetic division diagram, and we think, okay, this is what we're going to be dividing by, and then we're going to get something out with a remainder of 0 in the end. What we're dividing by is, and then this part that we get is actually going to be the other factor other than x minus 1. So that'll be nice on our way to factoring. So we think of, if we're dividing by this and using synthetic division, we just use a positive 1 right here. So changing the sign of that, negative 1. We're down the coefficients of this as 4, 3, negative 3, and negative 4. I'm going to come over here and just erase my little box because I drew it over there. But we'll put it back right here. Okay, so we drop the 4. 4 times 1 is 4. Then we get 7. 7 times 1 is 7. We get 4, and yay, look at that. 0 just as desired. X minus 1 is a factor. And we know we get this other part. So looks like it factors as x minus 1, 4x squared plus 7x plus 4. Now, okay, looking at this, okay, so we want to figure out, kind of do a sign analysis of this thing and seeing what's happening with it. Now, where is this quadratic right here equal to 0? If you want, we can use my technique for completing the square versus, or solving a quadratic, simplified. Maybe I'll look at that for a minute. So, if, just like in the last video, 4, 7, 4, and we think a little synthetic division diagram, we half this guy, we drop that guy, we think 7 halves divided by this guy, change the sign. 7 halves divided by 4, you're multiplying the 4 to the denominator, it'd be 7/8, change the sign, negative 7/8. And then you say negative 7/8 times this guy, and you put it there. So that would be what, negative 49 over 16. And then you're going to get something here. Now, notice that you end up getting a positive number because 49 is not quite 4 times 16. 4 times 16 is 64. So you're going to get a positive number here, which is bad because in the square root, you're always going to get this guy divided by that guy, which is also positive, and then change the sign to a negative. Oops. Okay, that means that this has two complex solutions that have imaginary parts that are non-zero, which means that this part yields nothing for our critical points, and in fact it never hits the x-axis, which means it never changes sign. So what sign is it? Well, just plug something in and it's never going to change the sign from there. Well, if you plugged in 0, notice you're going to get +4. It's always positive. So you can just think of this whole bit as just being something positive. So for our sign determining polynomial, you can just pretend like it's not even there. So really we only have x minus 1. This is times a positive number. So you think we can graph x minus 1 as a positive slope, goes like this, and it crosses at x equals 1. So it looks like this is the graph of our derivative will look something like this as a graph, kind of roughly. At least the sign determining part. So maybe I'll do maybe a little squiggly for me. It's not exactly the graph derivative, but it has the same signs as the derivative graph. So you think derivative's negative over here, positive over here. The original function then must be decreasing and then increasing. Oh my goodness, that is a minimum. So at x equals 1, we do get a minimum distance. So x equals 1 will yield a minimum distance. And it looks like it'll be the absolute global minimum overall with this particular sign analysis for decreasing and then changing to increasing. And that concludes this example. Look back at the last example. If there were some things in here that didn't seem quite clear, what in the world was I doing? I'm using ideas that I have in other videos too, so please look over my playlist if you're interested in seeing any of those. Thanks for watching.